So in this video, we're going to look at predicting precipitation using these solubility products. And so this is a different way of thinking about it, but it's complementary to what we've done before. So the KSP reaction, remember, if we've got something like calcium fluoride, and we say it's got a KSP of 1.46 times 10 to the minus 10, what we're really doing is saying that this equilibrium here, okay, between the solid and its ions has an equilibrium constant given by 1.46 times 10 to the minus 10. And so when it reaches equilibrium, then this is what we have. So let's spend a little bit of time and try and digest what this equilibrium is telling us. So first off, the equilibrium constant, which I'm going to hit with my green lightsaber here, right, is when things are at equilibrium. And by equilibrium, I mean that we have saturated the solution. So how would we saturate a solution? Well, the easiest way is just to take, say, some water and throw some calcium fluoride in. And the calcium fluoride will dissolve in water, and eventually, right, we will have a puddle on the bottom of calcium fluoride that is undissolved. So here we have, right, the equilibrium. So it's dissolving and undissolving. We've got that nice dynamic equilibrium going on. So once it's saturated, then if we take the concentration of the calcium ion and multiply it by the concentration of the fluoride ion and square it, right, at equilibrium, which in this case means that we are saturated, then this is equal to this equilibrium constant. And this special constant, right, we're calling KSP. All right, so far so good. Well, what happens if we are not at equilibrium? So how might we not be at equilibrium? Well, perhaps we've got a beaker, okay, and this is potentially not at equilibrium. And inside we've got some calcium ions and we've got some fluoride ions. And the question is, how do we know whether we're at equilibrium or not? And the answer is we calculate the reaction quotient Q. Because we're dealing with the solubility product, we're going to call it QSP. And QSP is going to be the actual concentration of those ions at that moment in time. So the actual concentration of calcium times the actual concentration of fluoride squared. All right, are we at equilibrium? Well, we're at equilibrium if Q and K are the same. So we're at equilibrium if Q and K are exactly the same. So that would imply that we have a saturated solution. So maybe we prepare a solution and it just coincidentally happens to be saturated. Now, perhaps we're not at equilibrium, in which case Q will not be equal to K. So maybe Q comes out to be less than K. Okay, what does this mean? Well, Q is the concentration of the ions multiplied together at this point in time. And if it's less than K, it's not at equilibrium. To reach equilibrium, these ions would have to increase in concentration. All right, how are those ions going to increase in concentration? Well, you have to add more to it. But unless you don't add more to it, there's no way for them to increase. What does this imply about the solution? This implies that the solution could dissolve more ions. So that means it is unsaturated. Okay, so more could dissolve if we wanted to. Okay, now if Q is bigger than K, so again, it's not at equilibrium. What does it mean if Q is bigger than K? Well, Q needs to get smaller to decrease to equal K. How do we make it smaller? Well, we lower the concentration of calcium and we lower the concentration of fluoride. How do you do that? Well, here's the reaction at the very top of the screen. We can lower those concentrations by shifting to the left. We're forming solid. And what do we call it when we take ions that are dissolved and form a solid? Yeah, we call it a precipitation. So this solution here would be supersaturated. Remember, a supersaturated solution may not be stable for very long. It can be stable for a few seconds to a few minutes to a few hours, but it will not be stable for the life of the universe. So if it's supersaturated, then it will eventually precipitate out. Sometimes this is instantaneous, so sometimes when we supersaturate, we immediately form a precipitate. Sometimes it just may take a few seconds or a few minutes. We'll actually practice this in lab. We'll make some solutions. Most of them will supersaturate and precipitate within about 30 seconds to a minute. Sometimes they're instantaneous, though. If the concentrations are really much higher, they can be instantaneous. So this is what I want you to get out of this. So the reaction quotient If it equals the equilibrium constant, the solution's saturated, no more can dissolve. If the reaction quotient is less than the equilibrium constant, it means more can dissolve, the solution is unsaturated. We don't have any more to dissolve, right? It just has to sit there impotently, right, wanting more to dissolve. But if Q is bigger than K, it's supersaturated. You've got too high a concentration of ions. We need to reduce the concentration of the ions by precipitating out. And so that's a supersaturated solution until it has a chance to form a precipitate.